Confounding always with the University of Technology. He's well known for his contributions to systems system identification. In 2016, he received an ERC Advanced Grant on network identification. And today he's going to talk about data-driven modeling methods.
Thank you very much, Kanat. Okay, good morning, everybody. Welcome at this talk. Can everybody hear me? Yeah? Okay, great. It's a great pleasure for me to be here. Thanks to the organizers. Where are they? How's Bing here? Yeah, Claudio, for having me here. This is the first time I'm present at a network control workshop. This one. And for me, it's very exciting to see the very rich problem field that is connected to network control. I gave this presentation also a couple of weeks ago as a plenary on the System Identification Symposium of Ifac, where the network part in that community is really new. I mean, people are not really thinking about this domain. So I hope in this session here to tell you a bit more about identification and how, from an identification perspective, people look at networks and how they can deal with that. You probably see some different frameworks and different model settings. I hope that you bear with me that I will take you through the story, see what we can achieve there. Okay, this is the starting slide. I noticed that it almost looks like the starting slide that Jorge had yesterday, giving examples of our environment where systems get interconnected in process control and smart power grids. The hydrocarbon reservoirs is probably new because I've been working on that domain for quite some years. And they also see different systems that are interconnected. Okay, let's not spend too much time on this. What is the trend that you see in the system control community, in the technology community? If you look at this from this picture, well, the dynamic systems that we handle become more and more complex, interconnected systems of systems. Of course, in this community, that might not be a surprise. With different types of dynamics, continuous, switching, hybrid. The related monitoring, control, and optimization problems become distributed of the multi-agent type. Data is everywhere. We are in the big data era. And the modeling problems will need to consider this. If we think about modeling the dynamical systems that behind that, we need to address this point. Yeah. So what will be our setups? Distributed or multi-agent type of control systems looking like this. Interconnected physical systems with controllers that also might be interconnected through communication channels. And there are both physical links here, the solid lines, and there are communication links in the dashed lines. Now the question that I was raising, okay, how do we address data-driven modeling problems in such a setting? If we look at our core expertise, our core methods and theories that we have available in the identification domain, then we typically look at problems like this. Open loop problems. We have a dynamical system, so think about G as, if you like to think in terms of state space representation, think about your state space representation there. Or your differential equation, G. We have inputs, outputs, disturbances. We measure U and Y. We like to model the dynamics of G. And in a bit more complex setting, we have a closed loop configuration where there's a controller present that controls the process, and we take measurements in a control situation, control configuration. For the moment, we will focus in this story typically on linear time invariant dynamics, but of course the story goes beyond that, yeah? In general. Now, if you look at the network setting, then we have to move from this fixed and known configuration to an area, a situation where there's way more structure into the problem. And that's what we're going to do today, to look at how we can exploit the structure and use this structure in our problems. Okay, I'll say a few words about the modeling setup that we choose for networks. I basically address two major problems, what I call single module identification of a local part of a network on the basis of data. I'll talk about network identifiability in the second part, and I'll briefly discuss some extensions if there's time, and of course I'll end up with some discussion. Yeah. Okay, so the modeling setup. Well, if you look around this workshop, then if people talk about networks, people typically talk about state space setups, which is the kind of natural domain for you to think about it. And from the identification perspective, people have been looking at these structures. I've mentioned a few authors here, but that list is definitely very much limited. If we look at the networks from a signals perspective, and we look at the typical open loop and closed loop configurations I just presented, then you could picture a network like this, where we have, the LTI systems, possibly with a controller around it, in all kind of structural connections with each other. And what we've been doing is using basically this setup like this to use as a basis for looking at our data-driven modeling problems, because it connects very easily to the things that we are used to and that we have available. Now, of course, the relation between the two can be made. That's not so very easy. Of course, the point is that this state space representation shows more of the internal structure of the systems, while what I call the modules in here, the LTI systems, can be of higher order state space dimension. So there can be states in here that are not directly, let's say, measured or accessible through the external terminals of the system. Okay, the relations between the two can be exploited. Lisan Kivis has been writing a paper about that for CICIT just a couple of weeks ago, presented. Okay, so what is our setup? So this is what I call the prototype dynamic network that I'm looking at. The G's, linear time invariant systems, typically represented by a transfer function. We have node signals, the W's, W1, W2, W3. These are the node signals. The circles basically are summation points, and the node signals, the W's, are the outputs of the summation points here. Now, typically we'll assume that the W signals will be measured, or can be measured. Maybe not all of them, but in this setting they will be measured. We have opportunities to excite our system. We have external signals that come in, inputs, that typically can be chosen by us. We can design them, and they might appear at different locations, R1 here, R8, R4, R5. And we have disturbances that we cannot control, disturbance signals V, that are just out there, typically modeled as a stochastic process, stationary stochastic process. And the disturbance signals might be correlated with each other, so they're not necessarily uncorrelated with each other. So there may be a disturbance structure still behind that presence of the V signals, where signals get interrelated. Okay, we have a total of L nodes. The network is well posed and stable. The modules, so every single element here is called a module, might be unstable. It can be stabilized by a controller. Disturbances are stationary, stochastic, and can be correlated. Okay, if we now write down the equations for all of these node signals, we write down the first node signal W1 as a linear combination of the inputs of the other node signals, plus some contributions from the excitation signals R and from the disturbances. And this matrix here typically gets a structure where it's basically hollow. There's a zeros on the diagonal. Why? Because we don't have any self loops there. The W3 signal is not dependent on itself. That's not a limitation. That's basically just a kind of scaling type of property that we impose. Okay, we just collect this together in a matrix G0. We have a matrix R0 over here, and we have the V. And of course, we can explicitly write the W now as a function of R and V. So we can consider R as an input, the V as an input, and the W's as an output measured. Okay, now if we define a setting like this, we can think of very many different types of data-driven modeling or identification questions. We can look at the problem, for instance, of just identifying one of the local modules here, how to do that. We can think about identification of the full network. We like to identify everything. We can focus on the topology only, which nodes are connected with which other nodes. We can think about sensor and excitation selection. Where would be the best places to measure if you like to achieve something? You can think about fault detection. Take the measure signals W, like to find out where one of the modules has run into a fault situation. Experiment design, distributed identification. I'll say a bit more about that at the end of my talk. So how we can distribute the identification problem, basically. And you can maybe add your own issues over there. Now, if you look at some earlier literature, people have started to look at topology detection, topology estimation in different settings. Donatello Materassi, I think, was one of the first to look in with the paper in IEEE transactions automatic control. A couple of years ago, people typically exploring notions of Granger causality, Bayesian networks, and sometimes also Wiener filters. Yeah. There's been some work done on in the subspace identification domain. People from Delft, Michel van Hagen and his team, looked at spatially distributed systems and basically also at algorithmic properties, how to design algorithms that can handle these larger scale problems in a structured way where we have identical models or non-identical ones. What we will be doing is to look at what they call the prediction error setting, prediction identification setting, and to focus typically on the structure aspects in the problems, and of course also including the non-measured disturbances into our framework. Yeah. So you typically see in this direction is that people typically assume that all the nodes are disturbed by white noises, and that makes life quite a bit more easy. Okay, so that's the setting. Yeah? So let's look at our first problem that we like to address. That's what I call the local identification problem. That reads as follows. We just point to a particular module here. We just pick the green one, and we would like to identify that on the basis of signals. And the question is, how do you do that? Now, maybe the naive answer to that question would be, okay, you just measure the input and the output of that module, and you use those signals for identification. Well, we know from closed loop settings, from closed loop identification problems, that we have to be very careful with that, because typically, because of all kinds of loops that are going around, that may not give you the right information. So the question is, which signals to measure, which signals do you need in order to get to a good estimate of the G210? That's one of the first questions to address. Now, how would you approach such a problem of identifying that local module? Yeah? Here's one option. You identify the full network, and if you have the full network, you also have the local module. So you could simply use this equation for the representation of your W's. You have R as a measured input, V as a disturbance. You could identify the transfer function from R to W. You have this setting and derive your module from that. Now, of course, that looks a bit like shooting with a cannon on a fly, because you have to excite everything. You have to, the whole network has to be in movement. Enough excitation should be there in order to identify your full network. So that's a bit overkill. Yeah. This, of course, can be done with, let's say, with standard tools. Yeah. If you would like to really go for a local solution, a local approach, only just using a subset of measured references and node signals, then we may need a new approach, a new setup here. Okay, so what will you do? You measure the input, you measure the output, identify this transfer. But actually, if you carefully look at the structure here, you see that this modeling problem is not what we call a single input, single output problem. It is actually a problem with more inputs. Because the W6 also maps to W2, and the W7 also, and the W3 also. So basically, the estimation problem is part of a 4 input, 1 output problem. It's not just a 1 input, 1 output problem. Now, of course, if all the 4 input signals would be uncorrelated, you could reduce your problem to a 1 input, 1 output and still arrive at consistent estimates. But since we have correlations between these signals all running through the network, that's not a trivial task to do here. Okay, but we can address 4 input, 1 output problems. We can use more or less standard tools for that. I'll just briefly mention 2. The most important one, what we typically do if we have a 4 input, 1 output problem where there's possibility that the signals are correlated, so they might be part of a closed loop mechanism. Then, let's say the default method to be used would be called a direct prediction error method, where we take the measured output, the W2, yeah, We take the measured inputs that we have, so in this case there are 4 of them. We parameterize the 4 transfer functions from each of the inputs to the output. And the theta is the parameter vector there. And we use a noise model H for characterizing the correlation structure of the noise signal. So this noise model gets in there with an inverse. We use a prediction setting, one step ahead prediction setting with a prediction error. We plug in the data here. We typically minimize the power of the prediction error and find our optimal thetas and therefore our identified models. Now this setup has maximum likelihood properties, so we can reach minimum variance. Properties cover our lower bounds on the conditions that the disturbances VI are uncorrelated over the channels. So that the V signals on the inputs and the outputs should be uncorrelated. It's an initial assumption. And we use all the excitation that we have available through the signals. As a kind of alternative, we have what we call a two-stage or projection or IV indirect method that basically constructs the prediction error in the same way, exactly the same formula. There's one difference. We're not using the signals W as inputs directly, but we first project them to the excitation signals that we have outside of the network. So we only use those parts of the input signal that are caused by the reference excitations. We discard the part of the signals that are induced by the noise. And that gives us some favorable properties here. I'm not going into details how you do that projection, but you can imagine there's a way to do that. In this setup, we have consistency. There's no particular need for noise models. We still can include them, but we don't have maximum likelihood properties. So we don't reach the minimum variance results. Why is that? Well, actually, we're not using the full presence of the input signals here because through this projection, we discard part of our signals that we still have available, but we're not using for identification. And so that means that we are not using the optimal signal-to-noise ratio that we could have available here. Okay, just keep the main structure here in the back of your mind. It's not going to play a real dominant role in my talk, but it will be. So we have a 4-input, 1-output problem. We can solve that. Next question, can we do with less inputs? Do we need all 4 of them? In order to check that, we use this principle of what we called network immersion. Arno Dankers used that in his PhD thesis 4 years ago. And the network immersion, we basically are removing nodes from our network. So we are going to construct an immersed network where some of the nodes are removed, and the dynamics in the disturbance structure is changed in such a way that all the node signals remain invariant. So we kick out a few node signals, but the ones that we keep, they exactly have the same signal structure as before. That means that we need to adapt some modules and disturbance signals. And it's basically an abstraction through variable elimination. And in network theory, it's referred as Cron reduction, we learned later, actually. So how does it work here? Let's suppose that we're going to immerse W7. So we're going to remove that from our network. How do we do that? So we remove it in this case. That means that all the interconnections between the node signals that run through W7 have to be replaced. We have to replace this one. We have to replace this one. And also we have to replace the disturbances V2 and V3 because the disturbance entering here, V7, is going to add to this node and going to add to this node. So we adapt those signals in such a way that the W's here are still the same as the W's over there. Now you see that in this immersing step, the G21 has been left invariant. So what does it mean? Well, then actually you could look at our identification problem in this setting and say, well, you know, in order to see which node signals map into W2, we have W1, W6, and W3. We have kicked out one of our inputs. And the dynamics of G21 remains the same. So it means that if we do identification now in this setting, we only need 3 inputs and 1 output. Okay, is that, can you Okay, can you build some theory on that? So the question then is, when does immersion, kicking out a node, leave a particular transfer function to a particular module invariant? Okay, I can build some theory for that. So we consider an immersed network where W1 and W2 are retained. These are the inputs and the outputs of the module that we would like to identify. Then in our immersed network, the dynamics is the same as in the original one if two conditions are satisfied. The first one is that every path from W1 to W2, other than the one that passes through the module of interest, goes through a node that is retained. Differently phrased, we should not allow for any parallel paths between our input and output that are not measured. I'll show that in a moment, how that works. The second one is every path from W2 to W2, that's a cycle, that's a loop, again also goes through a node that is retained. Why is that? Well, you can imagine that that if this one is not considered here, this loop, the W3 is not measured, then the actual mapping from W1 to W3 will contain the sensitivity of this loop. And therefore will change the transfer function of that module to 1. Okay, how does it work? Just a simple example. We have W1, we have W2. Are there any parallel paths? Yeah, this is a parallel path through W6. This is a parallel path. This is a parallel path. And we can essentially block these parallel paths by just including W6 now as a measured node variable, because then we've satisfied the conditions. So this is a solution, just measure W6. You see W6 contains all the parallel paths that are present. So if I measure W6, include it as an input, then I'm okay. Yeah? Now let's look at the loops around the output. This is a loop around the output, runs through W1, that's measured, so that's okay. This is a loop through the output. This is one. And of course, you can extend that to the right. But you see that you can block all these loops around the output by typically measuring W3. Then we check the conditions. So that means actually now that we can throw away, we can immerse all the other node variables out of our network, have this 3 input, 1 output problem, and have the dynamics of G21 invariant. So we can still identify it. Okay. So reduce from a 4 input, 1 output to a 3 input, 1 output. That's a step. This immersion reasoning, you can imagine, that's just one way of reasoning towards the problem. It's not a necessary condition to arrive at consistent estimates here. And Johannes Linder and Martin Enquist from Linköping have shown some alternatives for this. But actually at the moment we're working together with them to see how we can generalize the notions and merge the approaches together in one approach. Okay. Moving too fast now. What's happening? 3 input, 1 output model, we can identify the module of interest. But we can identify it with an indirect method, so our second type of algorithm. Because the first type of algorithm, the direct one, which leads to the best minimum variance, the maximum likelihood estimate, has one additional condition that we need to satisfy. And the condition that we need to satisfy is that we should not have any confounding variables in our problem. Now, what is a confounding variable? Confounding variable is an unmeasured variable. It refers to an estimation problem as an unmeasured variable that is correlated to both the input and the output of an estimation problem. It creates correlation between the input and the output, which is not induced by the module, but which is induced by the disturbances which are happening. Correlated disturbances in input and outputs. And these confounding variables are a bit tricky to deal with. So in this case, we could wonder, do we have any confounding variables? I'll come back to that in this example. Just look at the simple closed loop problem. This is a simple closed loop configuration. We can typically identify the G210 consistently by predicting the W2, use this as an output, this as an input, get consistent estimates. However, this procedure breaks down if the V1 and the V2 are correlated with each other. Now, if they are correlated with each other, what can you do? Well, actually, that means that the estimation problems of estimating the G210 and the reverse path get connected to each other. So that means that you should move from a single input, single output problem actually to a multivariate problem. Predict both W1 and W2. Build a predictor and prediction error, which is a vector now of two components, and consider both the prediction errors on the W1 side and W2 side. Then again, we arrive at consistent and minimum variance results. And this method has been developed as a so-called joint direct method, presented at CDC last year, but will also appear in Automatica later this year. It has close relations to what is classically called the joint I/O method for people who are more into the details of the identification approaches here. So what is happening here in this confounding variable mechanism? Suppose that we throw out W7 in our example. Then you can imagine that W7 has a path to W2. W7 also has a path to one of the inputs, and then it acts as a confounding variable because it's an unmeasured variable that correlates with the output and it correlates with the input. Yeah? So for the minimum variance type of results, if we like to stick to this multi-input single output framework, we lose consistency of the estimates if there are confounding variables. So what do we need to require? That means that the V7 and the V2 should be uncorrelated with the disturbances on the inputs as a start. And there should be no path from W7 to any of the inputs. If there's a path to any of the inputs, we typically can block that in this way. So suppose there would be a path somewhere through the network from W7 to W1 of the inputs, and there's a node along that way. We can measure that node additionally, block the effect of the confounding variable, and now again move back to a 4-input, 1-output problem, taking the W4 node as an additional input. Okay, there's a relation between these settings, this type of considerations of dynamic networks, and the notion of d-separation in graphs. I've been trying to explore that. We didn't reach yet the 100% understanding of the relationship, but we've come pretty close, working together with Donatello Materassi on this. But that's basically just some extent work in progress. Okay, so summary of the single module identification problem. We need to develop some new insights there. It's not solvable by just the standard tools. Of course, we work in this setting now with known topology, and we assume that topology is known, and we like to identify this particular module. We have methods for consistent and minimum variance module estimation. That's good. We have either excitation through the reference excitations only, or through all available signals that are present in our network, which is more strong. And there are maximum likelihood results, but we have to treat this confounding variable mechanism. And this confounding variable mechanism is relatively new in the identification setting also. We've not been used to dealing with those concepts yet, because of the structure, of course, in the networks. And of course, we can account for prior known modules. We started with a network where all the blue boxes are typically unknown. You can color the network in terms of blocks that you know the dynamics of and blocks that you don't know the dynamics of. You can address them also in this problem setting. Okay, second problem, network identifiability. And now we're looking not only at a particular local module, we will be looking at the full dynamic network. And here I did the coloring. Yeah. So we have the blue boxes which are unknown, the red boxes were assumed to be known. Right? You have designed them by yourself, you know what the dynamics is, you don't have to identify them. Now, one of the questions that you, I think, immediately can ask is, can we identify the dynamics of the topology of this network uniquely from measured signals R, so the reference signals, the reference excitations, and the W's? And And of course, in order to do that in a unique way, you could say, well, we have to address the question whether we can distinguish different networks from each other on the basis of the W's and the R's. And that's essentially what we could phrase like an identifiability problem. Do we have enough information in our data, R's and W's, in order to make unique statements about the network? And we will address this question firstly by assuming that all the W's and R's that are present in our network can also be measured. So they serve as a basis for our studies here. And later on, you can imagine that you could reduce that. You could say, okay, I just take a limited set of W signals available, because some of them may not be measured, for instance. Okay, let's go back to our equations. The W's, G naught, R naught, H naught. We have a covariance of the E, which is the white noise. So this is now the representation of the disturbances that we separate in a noise model and a white noise effective process with a particular covariance. The rank of E is P, the dimension of R is K. These numbers will come back in the future. We write the equation explicitly. Yeah. Take the inverse. Now we say, well, okay, we have a network which is now defined, the notion of a network defined by a quadruple of operators, the G naught, the R naught, the H naught, and then the covariance matrix of the noise, the lambda. So this is a network. We say, okay, a network model is just the same quadruple, but then the representation of that, G, R, and H with lambda. And the network model set is just a parametrized set of models. The model has these four checks. We have theta as typically a real valued parameter that ranges over a particular domain. We have a parameterized model set we call calligraphic M. This M represents the knowledge, the prior knowledge that we have on the network models. Yeah? So if we know the dynamics of particular modules, that is encoded in this model set. Yeah? We don't have to parameterize that module because it is known. It also represents the disturbance correlation. Yeah? The choice of our H matrix here will determine which disturbance signals we allow to be correlated and which signals we assume to be uncorrelated with each other. That's also encoded in this disturbance correlation. It covers known modules, and it also represents the signals used for identification. Oh, too fast. What's going on? Here, yeah. Okay, while writing this W explicit, we see that, of course, the W has an R as input, network transfer function object over here, and the disturbance is basically just a 1 minus G naught inverse times H naught times E. And we denote this as the TWE0. And the disturbance signal here is the spectral density that satisfies this equation. Yeah. Now, typically, if we have an identification problem like this, yeah, we have R signals available, W signals available, then the object that we can uniquely identify from that information is the transfer function TWR. If we provide enough excitation to R, we can identify this object. And since we are working with identification criteria, typically take a look at second-order moments of signals, we also can uniquely identify the spectral density of the V bar, this notion. So input-output transfer, you could say, of the network, and the spectral density of the disturbance. Now, how to define identifiability in this setting? If you look at the classical, well, there are very many definitions about identifiability, of course, in the literature. I think the very classical ones look at basically at consistency properties. Can I recover my original plant? The more modern concept in the identification literature treats identifiability as a property of a model set and looks at the mechanism whether there is a unique mapping between parameters and models in the model set. So when I can uniquely represent a model with a parameter vector. In this study, we are not so very much interested in unique parameter values, but we will be looking at unique models, which are more relevant for us. So what we're going to do, we're going to define it as a property of a model set still, but look at the unique mapping between models and identified objects. So these are the things that I can uniquely extract from my data. And then the question is there unique mapping between these notions and the models that we have in our set? If that's not the case, you will never be able to retrieve unique model representations. Okay, same formula. These are the objects that we can identify. These are the parameterized versions of those objects. Yeah? You just follow the original expressions over here. So here's the definition. A network model set M is network identifiable at a particular point in the model set. If for all other models in the set, equality of the two notions that we can uniquely identify implies equality of the models. And again, notice here that we do work with parameter values, theta 0 and theta 1, but they only serve as vehicles to represent models. We're not looking at the parameter levels. And so typically in the classical definition, here would be theta 1 and theta 0. We're not requiring that. Only the models should be the same. Okay, and if we require this for all the models in the set, then it's not anymore a local property, and it becomes a global property. Yeah? So it's network identifiable if it's for all the models in the set. Okay, so can we derive some theory on this? Let's first consider, let's say the first situation that we consider, K plus P is larger or equal to L. Again, what was K? K was the number of reference excitation signals. P was the number of independent noise sources that we had. So this, you could say, is the number of independent external signals, either R signals or noise signals. Suppose that the number of independent external signals is at least as large as the number of node signals that we have. That's a bit of overkill, you could say. That's kind of a luxurious situation. What kind of result can we derive here? Based on an earlier work of Joko Gonsalves and Sean Wannick, 2008. The M is network identifiable at a particular point. If now we take the R matrix and the H matrix, so that's the representation of the external reference signals, this is the noise model, put them aside into a combined matrix, they're parameterized. The condition is that we should be able to find a rational and non-singular Q, which is independent of theta, which transforms this matrix to having a leading diagonal structure. The leading diagonal structure which has to be full rank for all the thetas for which the closed loop transfer functions are equal. Yeah. Now if you look at this condition, you see that it's dependent on R and H. It's not dependent on G. G is actually the part of the model that encodes the topology of the network. So here, any topology is assumed. G can be fully unknown. There's no prior knowledge of the topology. Let's look at a quick example here. So here's a network where we have 2 reference excitations, 3 disturbance signals, and we have from prior knowledge, we make the statement that we allow the V1 and V2 to be correlated. So the V1 and V2 could be correlated with each other. That means that if you start modeling the disturbances, then your H matrix will look like this. You have V1, V2, V3, V1, V2, V3. The V1 and the V2 are allowed to be correlated. That means this matrix is full. The V3 is independent from the previous ones, has a structure like this. And then the R points to the presence of the references for L4, R5, reflected in these ones. The G can be fully parameterized. So it means that you don't know anything about the topology. If you combine so these are the mechanisms there, or 4, or 5. And of course, you can clearly see that if you combine those matrices together, 5 by 5, you can never manipulate the columns in such a way that this becomes leading diagonal because of this correlation structure. So the information that we have now that V1 and V2 might be correlated is an essential ingredient for the identifiability study. If these two would be uncorrelated, V1 and V2, this can be parameterized as a diagonal and we satisfy the condition. That means that under those excitation conditions, you could uniquely find the topology and the dynamics of the network without any prior knowledge about the structure. So a simple test is this. The condition is typically satisfied if each node in the network is excited by either a reference signal or an independent noise signal. Kind of makes sense. But the result, of course, is also rather conservative, restricted to that case that we have at least as number external signals as we have node signals, and we cannot account for any prior knowledge in G. So if we had some red boxes there, we cannot encode that in this result. So we'd like to make one step beyond that and see if we can find conditions that also include the structure of the G. So this is a more general result here, theorem. Two minor conditions. Each unknown entry in M covers a set of all proper rational transfer functions. We don't have any limitation on the model order here, on the model size. And all unknown entries in the model are parameterized independently, so there are no relations between dynamics in the modules and dynamics in the disturbances. Then the model set is network identifiable at a particular point. If and only if now two conditions are satisfied. We look at the combined matrix of G, H, and R now. So this is including the network dynamics. Each row should have at most K plus P parameterized entries. Again, K plus P is the number of independent external signals. And as a technical condition now, for each row I, a particular transfer matrix has to have full row rank. Now, what is the particular transfer matrix? Well, we look at the particular row of G, H, and R, the ith row of G, H, and R. And we look at which elements there are parameterized, that are the stars, and which elements are fixed. These are the zeros and the ones. And the transfer matrix that has to have full row rank here is the transfer from external signals that are not parameterized, so the zeros and the ones, to node signals which are parameterized. In this case, W2, W4, W5. So the condition is the transfer matrix from these external signals to these internal signals should have full row rank. What does that mean? Again, we look at the same example. Now we restrict the structure of G. We don't allow everything to happen here. And just for ease of reference, we choose the structure which is also present in the real network that we have in hand. We have the same H and R as before. We have to check the condition. On every row, we should have maximum K plus P, the number of parameterized entries. K plus P is 5. That's the dimension of H and R. And so you see that that condition is satisfied. We don't have more than, in this case, more than 4 even. Yeah? That's okay. We could allow even more parameterized entries there. Now we look at this technical condition of this transfer. Look at it from the first row perspective. Right? That means we look at the output W1. We look at the transfer from the disturbance signals which have zeros here. Yeah? The mapping to the W2 and W5 here. So that's the mapping that we need to study. Yeah? Again, look at the example. The red nodes are the 2 outputs that we consider. The red arrows are the 3 inputs that we need to consider. So the mapping from the 3 inputs to the 2 node signals should have full row rank. Now, how to analyze that? That's not so very easy to analyze in general. But we can use a bit of a classical result of Jacob van der Woude, 1991, and picked up also by Julian Hendricks in his contribution to the CDC last year. Looking at the generic situation of that matrix, basically. You can say, well, the generic rank of a transfer function matrix between inputs R and nodes W is equal to the maximum number of vertex disjoint paths between inputs and outputs. Okay? So definitely in the identification environment, I would need to define these vertex disjoint paths. So let's look at, so these are the set of inputs and outputs. What is the number of vertex disjoint paths here? This is one path, this is second path, this is the third path. They don't cross identical nodes here. So in this case, we have generic rank 3 of this matrix. And now if you look at the example that we had, 3 inputs, 2 outputs. This is a direct connection from input to output. And we have a direct connection here, there. They don't cross through joint vertices. So that means that we have a full row rank of 2 in this case, and we are identifiable in a generic sense. Okay? So that's what we pay for it. You have to analyze it generically now. Imagine what happened if this feedback loop was not going through W2, but going through W4. Then we would be in trouble, because then W2 would not be able to be reached without going through W5. Okay? So if this arrow would go to here, we would lose identifiability with this condition. Yeah, so in this case, we are okay. Yeah. This condition has to be checked for each row. That means basically for each node of our network. So it's not, in that sense, not so very simple one to do. We can do it in an analysis way. Formulating conditions under which it is satisfied for all nodes is I think, still an open problem, where we would like to specify, okay, where do we need to put the reference excitations in order to satisfy the condition for all the different nodes. Yeah, so you can say also, well, in order to have this full row rank condition, we need to have a situation that the number of unknown modules in G for every row should be smaller than or equal to the number of external signals uncorrelated with the noise on that node. So that's a kind of general rule that we need to satisfy in order to be able to have this full row rank condition. Okay. So summary of this identifiability concept. So this identifiability now is basically determined by the presence and location of external signals. Where can we excite the network in order to get our information? The correlation structure of disturbances. How do we allow the disturbance signals to be correlated? If we assume that they all are uncorrelated, then that's additional information that would help identifiability. But of course, that depends on the situation that you're having. And prior knowledge of modules. If you know modules, they become red. You don't have to parameterize them. That also is really a core element in the reasoning now. Okay. So far, you consider situations where all node signals are assumed to be measured. Our analysis and our theory is fully applicable to the situation that P is smaller than L. What does that mean? We call that so-called reduced rank noise. That means that the number of independent white noise sources that we have is strictly smaller than the number of disturbance signals that we measure. I'll say a few words about that in one of the following slides. And we look at, so far in this theory, we look at identifiability of the full network model. We basically look at the full-sized network. Although the conditions that we derive are row-wise conditions. So you could say, well, actually, the identifiability is built up of identifiability of all the transfers towards each particular node separately. It's already kind of distributed mechanism. Extensions, which are possible, but you could relate back this also to state space structures again. Some people, typically also Jorge Gonçalves in Luxembourg, has been working on that, published in the Transactions paper 2017. That relates to this. Some recent developments, work of Julia Hendricks and Michel Gevers and Alex Bazanella recently, where they have been looking at a related problem where we don't assume all the signals to be measured, but we assume all the nodes to be excited by reference signals, which is a kind of particular excitation setting. And then looking at the identifiability of a particular module, a single module, not a full network, but a single module. You can also do the reversed way, saying, well, I still measure all the node singles, but I look at particular excitation locations and look at the conditions under which one particular module is identifiable. And Harmeers has been doing that now for CDC. And of course, the best thing to do would be to combine the best of both worlds and to have local module identifiability on the basis of a selected number of measurements and excitation signals. So somehow we are not there yet, I believe. No, it's a bit of a tricky thing. Okay, so far for the identifiability problem. A few words about some extensions of this work. I already mentioned it, the situation of reduced rank noise. We have been thinking that in the typical data-driven modeling frameworks, you measure some outputs of processes, and then you assume that all the outputs are having some disturbances when you measure them. And the disturbances are always full rank. That means that the disturbance always can be modeled as a noise model having white noises as inputs, where the number of white noises is equal to the number of disturbance signals that are present in the network. Now, of course, if the size of these networks is going to increase, you can imagine that the assumption is kind of maybe one which is too severe. So we've been looking at situations where this number of noise sources is strictly smaller than the number of disturbances. And how to deal with that in an identification context. We call that reduced rank noise. And it is typically present in what we call dynamic factor models. To a large extent used in econometrics. We also look at joint sources of mechanisms that you could measure in dynamical models. I'll just be very brief here. I think I have 2 slides. Just show the results of that mechanism. So what typically would be if you have an estimation problem with multiple outputs, you would look at as an estimator which minimizes a quadratic function of your prediction errors, epsilon here, weighted in a particular form, Q. Yeah? And the weighting matrix here is important if you would like to achieve Kramer-Rao lower bounds, minimum variance type of results. Yeah? So these estimators typically lead to consistency under some regularity conditions, but for minimum variance probability, an optimal Q has to be chosen. And how to choose the Q typically? Well, typically you choose the Q as being the inverse of the covariance matrix of the white noise that underlies your data. Now, in this particular case, this covariance matrix will be singular, so you cannot invert it. So there's not an easy way to calculate this, let's say, minimum variance type of estimate. Because, okay, what is the effect of that? What is the result of that? Actually, you can parameterize the dependencies in the innovation process. So the fact that you have smaller number of white noises in relation to the disturbance signals shows that there are some dependencies in your innovation. You can include them, parameterize them as constraints, and then your identification criterion actually changes from the typical quadratic type of optimization problem to a constrained quadratic optimization problem. And the presence of constraints helps you to include those rank mechanisms of your noise. And we still have maximum likelihood properties for that constrained quadratic problem for Gaussian noise. You can formulate Kramer-Rao bounds again for that same situation, and the theory just continues, which is, I think, very nice. And actually what you see is that if some of the parameters are determined by this rank mechanism in the noise, you can estimate them even variance-free, which was kind of surprising, but it completely fits with the theory. Okay, this contribution is the first presentation at the Ifac World Congress, and will appear in Automatica later this year in a paper by Harmeers. A second topic is sensor noise. So at this moment, when we started our framework, I said, well, we assume that all the W's can be measured, but the W's can be measured typically noise-free. There are disturbances present on the W's, but you measure them in a noise-free way. So what would happen if you would start adding sensor noise to your measurements? And that means that we do something like this. We add sensor noise to the measurement of W1. We create a measured W1 tilde. Do that for the same. The pictures become a bit more tricky. Dealing with these sensor noise configurations is a typical hard problem if you look at open loop type of problems. They lead to problems which are called as errors and variables problems in estimation. And they're typically tough to address. Now the fun thing here is that in these dynamic networks, dealing with sensor noises may become more easy than in a simple open loop configuration. Why? Because there are many different variables running around in your networks that you can measure and that cover to some extent the information also about the variables that you are interested in. So there's a solution strategy here where we can apply a kind of a correlated or instrumental variable type of approach to mitigate the effect of sensor noise. For instance, you can imagine that if you have enough excitation present in your network, your measured variables will always contain part of the mechanism which is caused by the reference signals and something which is caused by the sensor noise. And since these effects are uncorrelated, you simply might project the sensor noise out. That's one mechanism you can apply. And as a result of an algorithm where you combine a correlation approach to remove the effect of sensor noise and use both Jenkins noise models for addressing process noise. And that has also been published in an Automatica paper 2015. Just with the message, hey, sensor noise problems might not be as hard as we imagined at the start. I'm there, almost. Okay, some reflections looking back. We have 2 minutes left. Dynamic network identification, we entered into an area where I think there are a whole bunch of problems to be addressed in a new setup. I find it quite an intriguing research topic. And of course, we call the linear time invariant framework is just the beginning. I also refer to the centralized LTI framework because I would say from your perspective, you see that I consider in these estimation problems, I still consider all the data to be available somewhere centrally. And there's a central coordinator which can do all the calculations. And of course, it would become different if you think, okay, what kind of information is present where? And how can we address that? We're moving from classical prediction error methods to more machine learning type of approaches, regularized kernel-based approaches, because typically in identification, if we think we do the identification, we have to choose a model set. We know that we have to estimate different modules, and they all will need to be parameterized in a way that they are exactly covering the reality. Now, you wouldn't like to do that in a large-scale problem. And machine learning tools are quite attractive in order to address that. Some first contributions being made there. We'll be expanding on that. Yeah, so further move towards data aspects related to distributed identification. That's what I'm referring to here in the centralized case, and of course also to distributed control. We have not been talking about algorithmic aspects, because if you like to see increase of scale and complexity, then we have to move also away from the classical algorithms that we have been using for small-scale problems. And well, there's a first contribution towards including nonlinear dynamics and detecting where in the network nonlinear dynamics could be present. Martin Schaukens has been making a contribution there in society. And last but not least, thanks to my co-workers and colleagues and students for this particular work, in particular Arne Dankers, who graduated in 2014, is now in Calgary, has been playing a major role in this work, and Harm Weerts, whose thesis is now finished with the committee, so he's finishing up in a couple of months. They both have been carrying out this research dominantly, so thanks to them. Thank you very much.
Like this? Oh, okay. So, Paul, I wanted to ask you about whether you have considered scenarios with latent nodes, right? So nodes where I don't know that they are there, but somehow they are mediating, right?
No, we have not been considering this, but of course, to have the, let's say, the kind of fixed structure in our network basically has just been a starting point to get the problems addressed. But that would definitely be one of the issues that would have to be added to our list of interesting topics to address. I've never considered that.
Yeah. Even related to that, the idea of maybe not specifically identifying, connections from node to node, but between aggregations, right?
Yeah. So in essence, you could see the single module identification problem just as a way to look locally, and that locality, of course, could be bigger than that. Yeah, as a kind of a subnetwork.